Now today in class 12th, I will tell you about the magnetic field on the axis of a current carrying circular coil. This is a very important topic because this is asked many times in the board exam, and also certain questions are asked in the NEET exam. So this is a very important topic. This is the circular coil. This is the axis. This is the point P of observation. This is at distance x from this center. So this let A equal to radius of coil. So this is now radius. This is radius A. Now let it carries the current I. I equal to current in coil. Let OP, this is equal to X. So to find the magnetic field at the point P, we consider two diametrically opposite elements. Let this is the element N here, and this is the another element. This is now suppose element M, this is now suppose element N. This is of length dl, and this is like this PM, this is equal to R. Consider opposite elements M and N, each of length dl. So this length is dl, this is now length dl. Here we take this M and this is now length dl. This length is dl. So what the angle that makes this dl with this line OP, that will be equal to 90 degree. Similarly, here we have this is also known R. The magnetic field because of these two elements M and N, that will be in this direction. This is the magnetic field dB. Since both the elements are at equal distance from the point P, so they will have the same magnetic field. So magnetic field at P due to elements, this dV equal to mu naught upon 4 pi into I dl sin pi by 2 upon r square. If we have this tangent, this you can suppose that I am taking this coil just in this way. So if we take the element here, that this will make an angle of 90 degree with this line PM. So because of that I am taking here, this is not pi by 2. So dB equal to mu naught upon 4 pi into I dl upon r square. This is an angle alpha. So this angle will also be equal to alpha. If we draw a line perpendicular to this axis OP, like this one, then this angle will also be equal to alpha. This angle is also equal to alpha. Now then we can increase to this one in this direction. So we can have the components dV cos alpha and here also this dV cos alpha. Now here the component dV sin alpha and here this is also dV sin alpha. dV sin alpha. So you can have the components. Components of dV. So this is now your dV perpendicular, this is your dV cos alpha, and this dV parallel, this is now your dV sin alpha. The parallel components are these, perpendicular components are these. So the components which are along the axis, they are the parallel components, and the components which are perpendicular to the magnetic axis, this axis of the coil, they are the perpendicular components. This is not dV perpendicular, this is not dV parallel. So now you can see that the sum of these components dV cos alpha, that will be equal to 0. So we can have a large number of diametrically opposite elements. Resultant magnetic field of dV perpendicular components, this is equal to 0. So there is no magnetic field perpendicular to the axis of the coil. It means there is no magnetic field perpendicular to axis of coil. No magnetic field means if suppose some charge is placed on this line which is perpendicular to the axis of the coil, that will be equal to 0. So no force will act on this line perpendicular to the axis of this. So now you can have that the only components that are left which are now dV sin alpha, and you can see that there are number of diametrically opposite elements. So because of them the magnetic field will be only along the axis of coil. considering all diametrically opposite elements of coil, the magnetic field will be along the axis of coil. इसका मतलब क्या है कि अगर यहाँ मैग्नेटिक फील्ड निकाले तो इन सब का सम कर दें. So sum of all these components which are parallel, now dv sin alpha, this will not be equal to 0, but this will be added up, because all the magnetic fields, because of these all the elements, that will be in the same direction. Therefore, resultant magnetic field B is equal to the sum of all these components dv sin alpha. So this is equal to sum of mu naught upon 4 pi into I dl upon r square into sin alpha. And this is mu naught upon 4 pi into I upon r square summation dl into sin alpha. This sin alpha, that will be equal to a upon r. A upon r. Sin alpha equal to a upon r. That you can see from the right angle triangle. So this is mu naught upon 4 pi into I upon r square summation dl. This is not 2 pi a into a upon r square summation dl equal to 2 pi a, the circumference of the coil. So now this 2 pi will cancel by 2, and this will be your mu naught I a square upon 2r square. This is equal to b. This we have taken only one turn on the coil. If suppose there are n turns, for a coil of n turns, b equal to mu naught n I a square upon 2r square. This is now a upon r, a upon r. So this is r cube. This is r cube. Now the value of this r, this is equal to square root of a square plus x square. So you can write down this value here. Then it will give you b equal to mu naught n I a square upon 2 into a square plus x square whole raised to power 3 by 2. 3 by 2. Now this is not magnetic field. This is the magnetic field at the point P, which is at distance x from the center of the coil. So now you can have some special cases for this magnetic field. The special cases. Let M equal to magnetic moment then this is equal to Ni into A. So this is Ni and this is now your pi A square. A the area of the coil, pi A square. So we can write here that the magnetic field, therefore this B equal to mu naught upon 4 pi into 2m upon R cube. We can write it like this. This is not in the terms of the vector. This is a vector quantity. We can also express it in terms of the magnetic moment. Now some special cases. Now in case of special cases, first we take when x is very less than a. X is very less than a. So we can neglect the term x or x equal to 0. If x equal to 0, then what will happen? This is not 0. So this is not so much. B equal to mu naught Ni A square upon 2a cube. This x is equal to 0. So this is now a cube. Now this a square will cancel to this one. So this is equal to mu naught Ni upon 2a. So this is what the magnetic field at the center of the coil. This is now B naught. Magnetic field at the center of coil. So this is denoted by B naught. This is the maximum magnetic field. It is maximum magnetic field. Magnetic field. So it means that at the center of the coil the magnetic field is maximum. So we can also write it to B maximum or this B naught. Now, second case, when this x equal to plus minus ay on both sides of the coil. for x equal to plus minus a by 2. The p is equal to mu naught n I a square upon 2 into a square plus a square upon 4 raised to power 3 by 2. So this will be how much? This is now your mu naught n I a square upon 2. Just to solve to this one, so is now 5 by 4. 5 by 4 a square raised to power 3 by 2. So this will be your 4 2 and this is now 8, so this is now 4. So 4 upon 5 root 5, and this is your mu naught n I a square upon a cube. So this a square will cancel by this a cube. So what we have? This is now your 4 upon 5 root 5 mu naught n I upon a. This we can write down it to be a. Now in terms of this one, you can have to this value will come out to be 8 upon 5 root 5 into mu naught n I upon 2a. So mu naught n I upon 2a is equal to v naught. So this is, if we put the value of this one, then this comes out to be 0.716 into v naught. This is your what? The v naught. This mu naught n I upon 2a. This is equal to v naught. So now then you will see that and for case number 3, for x equal to a, the radius of the coil, b equal to mu naught n I a square upon 2. This is now a square plus a square raised to power 3 by 2. So this is equal to mu naught n I a square upon 2. Just to solve to this one, this is now 2a square raised to power 3 by 2. Mu naught n I a square upon 2 into, this will be your cube. So this is now your 2 root 2 into, this is now your a cube. So now this will be cancelled by this one, and you can have this value to be mu, this is now your 1 by 2 root 2 into mu naught n I upon 2a. Mu naught n I upon 2a. So what we have? This is 1 upon 2 root 2 into b naught. This is equal to b. So you can see that this magnetic field is less than this one. So as we are going away from the center on the axis of the coil, the magnetic field is decreasing. This is for x equal to plus minus a. So we can see on both sides, on the right side of the coil and the left side of the coil. Now for x is very greater than a. First we have taken when the x is very less than a. Suppose we have taken x is very greater than a, then what will happen? b equal to mu naught n I a square upon 2 into Now in that term we will leave this a square term. A square will be less than, that will be not 0. So we are having this only x square raised to power 3 by 2. So this is now your b equal to mu naught n I a square upon 2x cube. 2x cube. Right? So we can express this. This is equal to mu naught upon 4 pi into, this is your 2m upon x cube. This is equal to b, where m equal to the magnetic moment. M equal to magnetic moment equal to, this is your n I into pi a square. Just I told you. So here you can see what? That this magnetic field is proportional to 1 upon x cube. So when the distance, as we go away from the center of the coil, the magnetic field always decreases. Now, it shows that magnetic field on the axis of circular coil decreases rapidly with distance x. So what we have? This b is proportional to 1 upon x cube. So now you can see from here that this is the magnetic field due to the current carrying circular coil on its axis, and this is what the different special cases which are to be taken, and also this is to be asked. And you have seen that the magnetic field on the line perpendicular to the axis of the coil is always 0. So there is no magnetic field on this line. So this is what about the magnetic field of this current carrying circular coil. Thank you very much.